Hello everyone, we are going to talk today about matched filters. As we know, in any communication system, a signal is being sent from a transmitter to the receiver via a channel. This signal gets affected by the channel noise before it reaches the receiver. Our problem here is at the receiver side. In the presence of the noise, it's impossible to recover the message perfectly. So to solve this problem, we use filters. A filter is a system or a process used to remove unwanted components from a signal. This process is called filtering the signal. At the receiver, the received signal S of t is being added with the noise component N of t as shown in the figure. In our case, the noise is AWGN, which means additive white Gaussian noise. This type of noise has uniform power across all the frequency band of the signal. The matched filter is placed before the sampling process. It is a filter that processes the received signal to minimize the effect of noise. Hence, it maximizes the signal-to-noise ratio of the filtered signal. The signal-to-noise ratio, or SNR, compares the level of the signal to the level of the noise. The higher the SNR, the better the detection. A matched filter is called so because its impulse response is matched to the input signal. It detects a piece of signal or wavelet that is contaminated by additive white Gaussian noise, as we can see in the figure. So the SNR is the square of the signal power over the square of the noise power. We wish to maximize this number by increasing the mean square value of the numerator, which is the signal power, and minimizing the undesired quantity of the denominator, which is the noise power, and this is achieved by the perfect impulse response of the matched filter. So let's talk about the impulse response of the matched filter with my friend.
After a lot of derivations and complex math, and by the use of the Cauchy-Schwarz inequality, we have found that for maximum SNR, the impulse response of the matched filter should be a reversed and delayed version of the input signal. So the impulse response should match the input of the filter, and that's why it is called a matched filter. Let's take, for example, the signal waveform of figure 1. In figure 2, we can see the mirror of the signal, and then we shift it to the right by capital T to obtain the signal shown in figure 3. So, for any signal S of t, the impulse response h of t is S of capital T minus small t. So, what's the output of the matched filter? The output is actually the convolution of its input S of t with its impulse response h of t. Convolution is a mathematical operation that does the integral of the product of two signals with one of the signals flipped. In other terms, it's the calculation of the overlap of the input signal S of t with the reversed impulse response h of t. As discussed before, the impulse response h of t of the matched filter is already the mirror of S of t. So, by convolving S of t with h of t is being flipped again and overlaps with S of t. Hence, it's like the signal S of t to be overlapping with itself as shown in the picture below. So, what is the output of such filter? Let's take a small example. Consider the input S of t is a pulse. So h of t is a mirrored and delayed version of S of t, which also gives a pulse. By convolving them, we get a triangular shape of maximum amplitude at t equal capital T. Now if we have a set of pulses as an input, the matched filter output is as shown. We have a tall spike at every positive pulse ending, as we see at t and for t. Now, how can we benefit from this process? We realize that the matched filter produces a spike at the sampling time if the received signal is a positive pulse. As we see here, if the received pulse is attenuated by noise, the matched filter will produce a spike at the sampling time, so we can perfectly detect the pulse without error. In other words, the matched filter helps increasing the SNR by making a signal which is below the noise threshold detectable. We can see in this example the 4 pulses will be perfectly detectable at sampling time due to the output of the matched filter. Let's look at the big picture now. A sequence of binary code is being transmitted. A 1 represents a positive pulse and a 0 represents a negative pulse. We're transmitting 11011 through an AWGN channel. The signal got obviously distracted by the noise. At the receiver, it is passed through a matched filter to minimize the effect of noise and for better detection of the pulses, and hence to increase the SNR. At the output of the filter, we can now distinguish the pulses due to the spikes. The filtered signal can now be safely sampled at the correct sampling instance, resulting in a correct interpretation of the binary message.